In the last series of lectures, we were looking at heat and mass transfer correlations for internal flows and for external flows. And I had said that these correlations depend upon a few different things. One is the flow regime. Whether it is laminar or turbulent. The second is what I will call the transport regime. That is low Peclet number or high Peclet number. And the third one was the interface conditions. Okay. So, these were the three broad factors that the correlations depend upon. Low Peclet number, of course, there is the convection is not important. The diffusion is dominant, and therefore, the Nusselt or the Schmidt number have to both be equal to constants. Okay. Okay. Now, at high Peclet number, the transport does depend upon convection, and in this limit one can further consider two different regimes. Okay. One is the low Reynolds number, and the second is the high Reynolds number. Okay. At low Reynolds number, the Nusselt number and the Schmidt number depend only on the Peclet number, because the flow is linear. The velocity at any point in the flow divided by the characteristic velocity. The characteristic velocity is the average velocity in a pipe or the free stream velocity for a suspended particle. That is a constant, even though the velocity itself changes. The ratio of the velocity locally, the velocity field at any point divided by the characteristic velocity is unchanged. And because of that, all the information regarding the velocity profile is contained within that characteristic velocity itself. And therefore, for a given configuration, the Nusselt number or the Schmidt number has to be equal to some function of only the Peclet number. Okay. And here, of course, there is no such guarantee. It depends upon both the Peclet number and the Reynolds number. Okay. And we had derived correlations for the pipe flow, for a parabolic flow in a pipe in the laminar regime. We got a correlation that was proportional to the Peclet number to the 1/3 power. Turbulent flow, Re power 0.8, Pr power 1/3 was the correlation times a constant. Okay. And I told you that the low Peclet number regime is not relevant for a pipe flow, because at low Peclet number it implies that the temperature or the concentration field diffuses across the entire cross section over a distance smaller than the pipe diameter. Okay. So, there is no point in having a long pipe in that case. Similarly, for suspended particles, we had got the correlations. At low Reynolds number and high Peclet number, we found that the Nusselt and Schmidt number were proportional to Pe power 1/3. Okay. Now, that Pe power 1/3 scaling we have seen in multiple cases in the flow in a pipe in the laminar regime, for example, as well as for the flow around a particle. Okay. And that scaling will actually be observed for all configurations where the interface condition is a no slip condition at the surface. Okay. Okay. You can have two types, rigid and mobile. And in rigid cases, you have, for example, for a solid particle, no slip condition. The fluid velocity at the particle surface is equal to the particle velocity. For a mobile surface, for a gas liquid interface, you have a zero shear stress. condition. Okay. Okay. For a gas liquid interface, for example, there will be a 0 shear stress condition at the interface. Okay. And we had seen those two conditions earlier. Okay. For a liquid film, for example, at the liquid gas interface you have a 0 shear stress condition. So, the slope of the velocity profile goes to 0 at that interface. The slope is related to the velocity gradient, which is related to the stress by Newton's law. So, if the stress is 0, the velocity gradient is 0 and the slope is equal to 0. Okay. On the other hand, at a liquid solid interface you will have a 0 velocity condition, that is that the velocity of the fluid at the surface is equal to the velocity of the surface itself. Okay. A 0 velocity condition for a solid particle, 0 stress condition for a gas bubble, for example. For a liquid drop you will have continuity of velocity and continuity of stress, in which case the velocity at the interface is actually non-zero in that case, because for a drop the liquid inside the drop can also move, can also circulate. Therefore, when a drop translates with respect to the fluid, there is a stress exerted at the surface which generates a fluid flow within the drop. Okay. And that has to be equal, the velocity of the fluid within the drop has got to be equal to the velocity of the fluid outside the drop at the interface. Okay. So, when we had this no slip condition at the surface, we found that the Nusselt and the Sherwood number were both proportional to P power 1/3, okay, P power 1/3 in the limit of low Reynolds number and high Peclet number. Okay. And I had given you some correlations for high Reynolds number and high Peclet number as well for that case. There the flow profile is complicated, and so you have a transition through a series of different flow patterns. Okay. Now, I will consider here what happens if you have a mobile interface. Okay. So, let us take the concrete example of a falling film of thickness h and length L, okay, in which fluid is flowing downwards at steady state. As I said, at steady state the velocity gradient at the liquid gas interface has to be 0. Okay. And what typically happens in this configuration is you have some species in the gas which has to be dissolved into the liquid, okay, scrubbing of a gas to remove pollutants, for example. The gas molecules of the pollutant diffuse to the surface, and since they are soluble in the liquid, they dissolve in the liquid. Okay. Once again, the low Peclet number limit is not of relevance here, because a low Peclet number would imply that the concentration of the gas equalizes across the entire film by the time it travels a distance comparable to the thickness. The reasoning for that is very similar to what we had for a pipe flow, and so I will not go into that in detail, but if the Peclet number is low, then there is an equalization of concentration across the film over a streamwise distance comparable to the thickness. Okay. So, there is no point in having a long contacting section. If I look at the limit of high Peclet number and laminar, okay, the correlation for the Sherwood number or the Nusselt number for heat transfer, okay, is of the form 1.38 Pe per half times h by L per half, okay, where the Peclet number is defined as the average velocity times the thickness h, okay, by the diffusion coefficient for mass transfer, equivalently the thermal diffusion coefficient for heat transfer. Okay. And this is valid at high Peclet numbers, so long as, okay, the for L by H is much smaller than P, okay, for L by H much smaller than P. Okay. This correlation is valid, okay, for a laminar flow. I should note here that the first of all, the scaling is different. Okay. It goes as half power, okay, whereas in the case of a pipe flow, for a laminar flow, we found the scaling as 1/3 power. Okay. And that is because of the difference in the boundary conditions between a rigid surface and a mobile surface. At a mobile surface, the velocity of the fluid at the interface is non-zero. So, as you approach the interface, the strength of convection is finite as you approach the interface, and you get a half power for the Peclet number. We will see later why that is true. Okay. We will actually derive this correlation later in while discussing unidirectional transport. So, at high Peclet number, for a mobile interface, you get a half power for the Peclet number for transport, okay, subject to this restriction. Okay. And I will just explain briefly why that restriction arises, and we will see this quantitatively later. Okay. Basically, when you have this gas diffusing, okay, into the surface from the liquid, okay, and the Peclet number is large, that means that the strength of convection is large compared to the strength of diffusion into the gas film. Okay. So, therefore, any gas that dissolves at the interface gets rapidly swept downstream due to the strong convection, and the dissolved gas is restricted to a thin layer, okay, called a boundary layer close to the surface. We will examine how this boundary layer grows as we go downstream, okay. But the analysis that gives rise to this equation is valid only so long as this thickness is much smaller than the H, okay, the thickness of the film. That is, the dissolved gas is restricted to a distance from the interface which is much smaller than the total thickness of the film. Okay. That leads to this condition on the ratio of the length and the height, okay, and we will do this calculation a little later in the class. Okay. So, you get a P power half for the flow in a film. You get the same thing for the flow around a bubble. Okay. If you consider a bubble of diameter d, okay, with liquid, okay, flowing around this bubble, okay. As I said, at the interface you have a slip condition for the velocity at the interface. Okay. We saw earlier that if you have a no slip condition, the Nusselt number and the Sherwood number are proportional to Peclet number to the 1/3 power. Okay. In this case, the Nusselt number and the Sherwood number, the correlation is 0.652 Pe per 1/3 for low Reynolds number. Okay. In the limit of low Reynolds number, the correlation is of the form Nusselt number or the Sherwood number is equal to 0.652 Pe per half. Okay. I told you that for a mobile interface, the correlation is always proportional to Pe per half in the limit of low Reynolds number and high Peclet number. Okay. For the flow past a bubble, you can also get a correlation in the limit of high Reynolds number and high Peclet number. You recall that I had told you that for the flow past a bubble, you do not see the kinds of patterns that you see for the flow past a solid particle. You know, the formation of a separation bubble at the rear, vortex shedding in the wake, the formation of a turbulent wake, and then the formation of a turbulent boundary layer upstream. Those transitions do not occur for a bubble moving relative to the fluid because of the mobile interface and the zero stress condition at the interface. Okay. Therefore, even in the limit of high Reynolds number, you can use a potential flow solution, okay, to calculate the velocity profile around the bubble. Okay. You do not have boundary layer separation and wake formation on the rear of the bubble. Okay. And therefore, I had, if you recall, I had written the drag coefficient for the flow past a bubble at low Reynolds number as CD is equal to 16 by RE. Okay. I should note here that this Beckley number, okay, the Beckley number is equal to the V free stream times the diameter by d or alpha. Okay. The free stream velocity times the bubble diameter divided by the mass diffusion coefficient for mass transfer, thermal diffusion coefficient for heat transfer. Okay. So, for RE small compared to 1 where CD is 16 by RE, you get this correlation. Now, for the other case where for RE large compared to 1 where CD is equal to 48 by RE, high Reynolds number potential flow case. Okay. In that case, the correlation for the bubble becomes the Nusselt number or the Sherwood number is equal to 1.13 Beckley number to the half. Okay. In both cases, it is proportional to Beckley number to the half. The only difference is in the coefficients. Okay. And these two coefficients can actually be calculated. We will see that calculation a little bit later. Okay. Okay, so, in the case of mobile interfaces where the fluid velocity is non-zero at the interface, the Nusselt number and the Sherwood number both are proportional to the half power of the Beckley number, okay, in this case. Okay. So, instead of the 1/3 power that we had for the flow past a rigid surface. Okay. And finally, the last correlation that I need to discuss is the heat and mass transfer for a packed column. Okay. If you recall, a packed column filled with particles, okay, and the fluid flows through the interstices between the particles. Okay. The fluid velocity, the superficial velocity Vs for the fluid is the velocity divided by the cross sectional area of the column. Okay. Vs is the fluid velocity divided by the cross sectional area of the column, and you apply a pressure drop across that column, okay, in order to generate a fluid flow, okay, through the column. Okay. So, Vs is the fluid velocity if the particles were not present. Okay. That is the superficial velocity. Okay. And if you recall, I had said that in order to write correlations for this case, we have to consider the characteristic diameter, the equivalent diameter of the voids between the particles, because the fluid is flowing through the voids between the particles. Okay. So, therefore, the surface area has to be the surface area of the particles, and the equivalent diameter has to be based upon the equivalent diameter of the voids, not of the particles. Okay. If you take the total volume of column as V, the porosity is equal to epsilon. Okay. Porosity is the volume of voids divided by the total volume. Okay. And particle volume Vp and surface area Sp. Okay. I'd said that the void area, okay, the void surface area, okay, okay. Notationally I should write this as AP. Okay. AP is what I had used earlier. Okay. Void surface area is equal to the particle surface area. Okay. Void surface area is the same as the particle surface area, because the surface is an interface between the fluid and the particle, okay, and the fluid is flowing through the voids. So, this will be equal to number of particles times the area of one particle. Okay. Void surface area is number of particles times the area of one particle. Void volume is equal to the porosity or the void fraction times the total volume. Okay. Void volume is the void fraction times the total volume, or the porosity times the total volume. Okay. Now, we do not know n, which is the total number of particles. This can be related through a relationship between the volume occupied by particles and the total volume of the fluid. Okay. So, the volume occupied by particles is equal to the number of particles times the volume of one particle. Okay. The number of particles times the volume of one particle. This volume is equal to 1 minus the void fraction times the total volume. Okay. The void fraction times the total volume is the void volume. Particle volume is equal to total volume minus the void volume. So, this is equal to the total volume minus the void volume, okay, is equal to V into 1 minus epsilon. Okay. Okay. Therefore, I can relate the number of particles to the void fraction and the volume of one particle. N is equal to V into 1 minus epsilon by Vp. Okay. And therefore, the void surface area is equal to n times the surface area of a particle, n into V into 1 minus, sorry, okay. That is the void surface area. Okay. And this can equivalent be written as 6 okay, because the equivalent diameter of the particles dE is equal to volume of particle by area of particle into 6. Okay. Okay. D is 6 Vp solution. Okay. That is the void surface area. Okay. The void surface area is equal to V into 1 minus epsilon by 6 dE. Okay. Therefore, the void equivalent diameter okay, dE void okay, is equal to 6 times V of void by S of void. Okay. Okay. And we had substituted this of dE for the volume of the void, okay, for the surface area of the void, and the volume of the void was equal to 1 minus epsilon into V. Okay. And if you use both of those, you will get this is equal to particle diameter epsilon by 1 minus epsilon. Okay. That is the characteristic size for the voids. Okay. So, this we had already done before. Okay. We had already done this calculation before to get the characteristic diameter of the voids and the characteristic surface area of the voids. Okay. The reason I went through this is because the Nusselt number and the Sherwood number, okay, are defined based upon the surface area of the voids, okay, is equal to the transport rate by void surface area, okay, the Nusselt number and the Sherwood number, okay, is equal to transport rate okay, divided by the void surface area, which is equal to yeah, there is a mistake here, it should be 6 times V, okay, by 6 V into 1 minus epsilon by dE. Okay, okay, this. Okay, because AP by VP by AP is equal to 6 by dE. Okay, so therefore there should be a factor of 6 here. Okay, so it's equal to the transport rate divided by this, the transport rate per unit volume divided by the 6 into 1 minus epsilon by dE. Okay, and the Reynolds number will be defined based upon V void times D void equivalent by mu, okay, which is equal to rho. The void velocity equal to the superficial velocity by epsilon, and the diameter is equal to d epsilon by 1 minus epsilon into 1 minus mu, 1 by mu. Okay. So, these will cancel out and I will get rho Vs dE by 1 minus epsilon into mu. Okay. So, that will be the definition of the Reynolds number. Okay. So, this we had actually derived earlier as well. Okay. Okay. So, here the correlation is written in terms of this Reynolds number and the Sherwood or Nusselt number, and the correlations have the same form as they have for flow through internal flows, except that now the fluxes are expressed in terms of the total surface area of the particles, and the Reynolds number is based upon the equivalent diameter of the void, not of the tube or channel, okay, as in the case of internal flows. Nevertheless, the form of the correlation turns out to be the same. One standard correlation in literature is Re power half plus 0.2 Re power 2/3 times pressure Prandtl number or Schmidt number power 1/3. Okay. Okay, so, these have exactly the same form that we had earlier, except that these are now based upon the Reynolds number based upon flow through the voids, and the Nusselt number and Schmidt number are per unit area of the surface of the particles. To calculate, to convert that into the transport rate per unit volume, you have to divide by this factor. Okay. To convert it into transport rate per unit volume, one has to divide it by this factor. Okay. And if you do those two, you will get this as the correlation, okay, for the transport in a packed column. Okay. So, so this completes our discussion of correlations for what are called diffusion problems, low Peclet number where convection is not important, and forced convection problems where the velocity field is specified and that velocity field is used for defining the Reynolds number, Peclet number, and so on. Okay. I will go through one final topic, which is natural convection, in the next class, and with that we will complete our discussion of correlations. Okay. So, I will continue this in the next lecture, and with a discussion on natural convection before we complete this section on correlations. I will see you in the next lecture.